storing this huge database might be a problem. Okay. So is there any other solution that you can think of? Right, so maybe searching is easier, but still storing would be the same problem, because you need to store in your hash table all these IP addresses, and there could be a huge number of them. Yes?
Those IP addresses, I mean, you know the format.
Yeah.
So, we can just use a try.
We can use that?
TRI, right, tree.
Okay.
So, the point of that is it will reduce the storage required considerably.
Yeah, so basically then maybe another way to implement your suggestion is that, say you have a list of IP addresses, and when an IP address comes in, you say that that IP address has visited, right? I mean, in some way you store, so either you store all the IP addresses which are visited, or you store maybe all potential IP addresses and you record which one of them have visited. Okay. But in any case, both of these approaches require you to store either the total number of IP addresses, which is huge, I mean something like 2 to the 64, which is maybe comparable to the size of the universe, or you store the total number of people who have visited, okay, which also may be very huge. Okay. So you want to do something which is, I mean, you want to keep in your storage some account of who have come, but that account should be somehow smaller than the number of total IP addresses or the total number of IP addresses who have visited your site. Okay. So this is the problem. So in streaming, streaming algorithms are generally concerned with this following setting. So you have a stream of items coming in. So here the stream was IP addresses which are visiting your site. Okay. But you want to find, you don't know when this stream will end, and when it ends you are given some task like find the number of distinct elements or something, and you want to be able to you want to be able to answer that question without having kept in storage the entire stream. So the problem is trivial if you keep in storage the entire stream, because then you can do some algorithm like those you suggested, right? But the question is, can you keep in your account some small, some compressed version of the stream that has come in, and then answer the question? Does it make sense? So in some way, human beings are like streaming machines, right? So we take in a lot of data, but in our brain we store some compressed version of the data. We don't store in all the details that we are seeing every day, but we store in our brain some compressed version of the data, and then we can remember, then we can answer questions about our past based on what we have stored. Okay. So that is basically the streaming model. So you have so this is your algorithm. And it takes in some stream. So let's call it A1, A2, all the way up to AM. Maybe let me write it in the opposite way. So A1, A2. Please let me know if this is not visible. I'll try to write a little bigger. Okay. So you have this stream coming in, A1, A2, A3, and then finally AM minus 1 and AM. Okay. And we'll make one last change. Okay, it's fine. AM, and the algorithm has a small storage space. Okay, small storage space compared to M, which is the size of the stream, or N. So N is the universe from which each of these tokens are being taken. So each AI is an integer between 1 and n. Okay. So in general, in applications, it may not be a stream of integers, it may be something else like stream of IP addresses. But anyway, we are going to think about it as integers because you can represent each IP address also as an integer. Okay. So just for the sake of discussion in this lecture, I am going to say that you have a stream of integers coming in. So you have m integers coming in, and each of these integers is between 1 to n. Okay. And your storage space is small compared to both m and n. Okay. And at the end you need to answer some question. So for example, number of distinct elements, or maybe something else. So we will talk about a variety of questions that you could answer and what you can say. So the specific problem I have told you, this number of distinct elements, it turns out that you cannot exactly say the answer every time correctly if you have storage space which is small compared to both m and n. So you need at least m and n, so your intuition is correct. Okay. But it will turn out that if we relax some assumptions, so if we are allowed to make a small amount of error, so if we are allowed to be 1% off in our count of number of distinct elements, which may be perfectly fine for your application, maybe your boss in your company doesn't care if you are only 1% off from the actual count of the number of distinct elements, and if you are allowed some small percentage of error, so it could be that with 0.01 probability you could be wrong, okay, 0.01% probability you could be wrong. But anyway, we take such chances all the time in our life, so we will ignore these things. So if you have if you allow some small probability of error and some approximation in your answer, then you can do much better than m and n. Okay, you can solve the question in log m and log n time. Okay, and log m is essentially optimal because even to store some number between 1 to n, you need log n bits. So if you need to store an integer between 1 to n, you need log n bits, right? So you cannot really hope to do anything better than log n because you need to store at least one token to see what's going on, and there is a solution which achieves this, and this is one of the most remarkable achievements in algorithms in the last 10 years, okay, that this kind of thing is possible, and I am going to tell you how to answer these kinds of questions. So first let's start off with a basic question. So this kind of question occurs often in job placement interviews. So this is also a streaming question. So for this streaming question, you don't need any randomization or approximation. Okay, so I said for solving this distinct elements problem, you need some approximation and some randomization. We'll come to examples of that later on. But right now, let me give you an example which is a non-trivial streaming problem, but it doesn't require both and may be more easily accessible to you right now. So suppose your problem is that you are getting a stream of numbers again between 1 to n, but you know that there will be, so in this problem you know that you will have n minus 1 numbers coming in. Okay, you will have n minus 1 numbers coming in and there will be one number missing. Okay? And you need to find which is the missing number. Okay. So obviously again you can solve the problem if you store all the the stream, and then at the end you can just go through the stream and see which is the missing number, right? But we want to do something faster. So we want to not store the entire stream, but we want to store some compressed version of the stream. By the way, so storing the stream in some compressed small storage space is called the sketch. So we say that we maintain a sketch of the stream. So small storage space compared to n, so it will contain, so this is a word that's used very often in the streaming literature. So contains sketch of this stream. Okay, again, so the problem is this, so you will have n minus 1 integers coming in, and we need to find some way to store it as a sketch such that we can answer the question what's the missing number. Do you have any suggestion for how to do this?
XOR.
Sorry. Yeah, good. So what was your suggestion? You can XOR, right? So both of, let me discuss both of these. So the first suggestion was that you store the sum of the numbers which have come in. Okay. So if the numbers were from 1 to n, the total sum would have been what? N times n plus 1 by 2. Okay. And now if you find the sum of these n minus 1 numbers, you can subtract that from n times n plus 1 by 2 and see what is the missing number. So that's a valid streaming solution. And so what is the complexity you need to store it? So you will need to store the sum of these numbers. So the sum of these numbers will be something like, n times n plus 1 by 2 minus something, right? So anyway, it will be of the order n square. So maybe n square by 3, or anyway, so something of the order n square. So in order to represent it as a sequence of digits, you will need about log n bits. Okay. So solution to missing number problem. So I will come back to the other solution discussed soon. So solution to missing number problem. Store sum of the AIs I equal to 1 to n minus 1. Okay, so this is your sketch. Okay, and then return. So when it's run, then you return. When the stream has finished running, then you return n times n plus 1 by 2 minus this sum. And the key part of this is that we can actually keep maintaining this storage incrementally, right? So every time an entry comes in, we just have to add it to the current sum. So this is a very important property. So it's very good if we store a linear function of the sum, because then what we can do is whenever a new entry comes, we can just add it to the entry, right? So in general, so suppose your we'll come back to this later on, but suppose your sketch is of the form A times X, okay, where X is this vector maybe. Okay. So then so there are different ways of implementing it, but we will come back to this. But then what you can do is, if you have a new entry coming in, you can just add it to, so then A times X plus A is going to be AX plus AA, right? So if you compute AA, and then you can just add it to AX. But anyway, we will see more clear realizations of this later on. But just to emphasize here that storing this sum of A1 to An minus 1, we can do it incrementally. Each time we just keep the current sum, and then we take the new element that's coming in and add it to what has already been stored, right? Good. And then, right, so this is clear why this works. Yeah, so the other suggestion was that you store somehow the XOR of these things. So instead of the sum, maybe the XOR. So here it's not clear because these are integers, how you can take the XOR of the integers. But let me tell you a context in which this is useful. So suppose these are not integers, but suppose they are string, each of them is a string of bits. Okay. So in this case, if you know that the total XOR has to be something, so here we knew that the total sum has to be this n times n plus 1 by 2. But if you knew that the total XOR had to be something specific, then you could keep taking the XOR of all the bits of all the strings that have come so far, and then so you know that you have to take so So the total XOR is something, and you have the XOR of n minus 1 thing. So to find the nth thing, you just have to add, you have to XOR also the target, okay, and then you would get the nth thing. Anyway, so I mean that is one way to do it if these are binary strings, but for integers this suffices.
Sir,
Yeah,
so can we also do it like this? Suppose we have n numbers,
yeah,
so we take n bits.
right.
Where ith number represents ith number will ith bit will be a sketch of ith number, and if a number comes with ith number I comes with on the ith bit to 1, and in the end we check which bit is 0, and then that number will be.
Yeah, so the problem with that approach, this is similar to the one of the approaches we discussed for the distinct elements problem. So the size of these numbers that you are storing, so these numbers are of length n then, right? Because you will have one bit for each thing, and n here suppose it's huge. So n is something like the number of IP addresses, or which is astronomically large. So you can't afford to store an n bit number. But here this sum only requires log n bits to store. So there is a huge difference between n and log n. So if n is 2 to the 64, then n is, I mean, like the size of the universe, and log n is 64, which is very easy, right? So so that's the difference. So we want to get from n bits of storage to log n bits of storage. Okay. Let me then ask you some follow-up questions. What about if there are two missing numbers, then what can you do? So suppose you have n minus 2 numbers, n minus 2 numbers which are coming in, and you know that there are two missing numbers, then how can you find? Yes. Great, yeah. So we know that the square of the sum of the squares is also something, n times n plus 1 times 2n plus 1 by 6, and you know that the sum is also something. So you get a system of, you get two equations and two variables, and you can solve that. And in general you can also do this for, I mean, if you have k missing numbers, then you can also solve the problem similarly. So you store not only the sum square, but you store all the way up to the sum of the kth powers, okay, and you get k equations and k variables, and you can find the solution in that way. And all of this takes about k log n space, because each sum you are each sum of powers you are storing requires about log n O of log n space. So you can do the whole thing in O of k log n space. Okay. So this is the first simple problem that we have seen, and indeed this is a valid streaming algorithm, because you are using much smaller space than, for example, the other algorithm that you described. Right? So the goal here is to, I mean, ideally if we can do something in log m or log n space, that's the best, okay? And this algorithm achieves this. Okay, so next let's move to a more challenging problem. So this is called the reservoir sampling problem. So here again, so the setup is somewhat different. So given, so stream is A1 through AM for unknown M. Okay. Another way to think about it is that you have an infinite stream, and then at some unknown point of time the stream breaks off. Okay. So you need to return, find a random element from A1 through A. What I mean by random is that the element chosen should be uniformly random. So there should be equal probability of choosing A1, A2, A3. So the probability of choosing any of them should be 1 by M. But the problem is that you don't know M. So you are seeing these elements, right? You don't know when this stream will cut off, but you want to find a uniformly random element from this, from the things that you have seen. Okay. So how would you do it? So again, the obvious approach would be you store A1 to AM, and then the stream breaks off. So you have A1 to AM, and then you uniformly sample from there. Okay. But now you don't know when this stream is going to break off, and you don't want to store everything because it could go on for a huge amount of time, and we don't want to keep in our storage a huge amount of things. So any suggestions? Great, yeah, very good. Yeah, so here is the algorithm. What's your name? Huh? Siddharth. Okay, so the algorithm that Siddharth suggests. So this is indeed called the reservoir sampling algorithm. So you select ith element with probability, with probability 1 by I. Okay. So the first element, when it comes in, you select it with probability 1, because if the stream immediately breaks, you just have to return that. The second element, when it comes in, you select with probability half. So you discard what you have selected so far, and you select that one with probability half, and so on. So let's analyze. So let's analyze what happens. So what is the probability? So suppose this stream breaks off at time m, after m elements, right? So let's analyze what's the probability of selecting some ai where I is less than equal to m. So we want to claim that the probability of selecting any ai should be 1 by m. Okay. Why is it? So let's see. So when ai comes in, so we have to put here. So probability of selecting ai, so given length of stream is m, is what? So the probability of selecting ai is 1 by I. And then it should be the case that we should not select ai plus 1 through am, right? Because if we selected any of those, then we would discard ai and choose the other one. So what is the probability of not selecting the I plus 1th element? It's 1 minus 1 by I plus 1. Okay, 1 by I plus 1 probability we selected it. So with 1 minus 1 by I plus 1 probability we don't select it. And similarly we have to take the AND of all of these things, and these are independent events, right? So 1 by I plus 2. Does this make sense? What this, how this calculation is being done? So this is the probability of select ith element. This is the probability that I don't select I plus 1, don't select I plus 2, all the way up to don't select m. So that at the end I have ai in my hand. Okay. So what is this? So this is a telescoping product. So 1 by I times I by I plus 1 times I plus 1 by I plus 2. And you see that all these terms cancel out except for this last m, okay, and this is 1 by. So again, this is a very classic algorithm which was developed before people coined the term streaming algorithms, but in retrospect this is a streaming algorithm. So actually, so I have talked about 2 problems. So I will talk about 2 more problems, and 3 of the problems were done before, say, the 90s, when the streaming algorithms was first introduced. And the last one, which is the most substantial problem I will talk about, is the one that was done in 2005. Okay, so this is also a streaming algorithm, right? Because each time you are just keeping in your hand one element. So the cost of storing that one element is log n, because so I am assuming that each number is between 1 to n. So the cost of just storing some number between 1 to n, you need log n bits. So you are keeping in your hand some log n bits of storage, and that's it. So again, this problem is somewhat different from sort of real streaming applications, because here again you don't have any error and you are not doing any approximation, you are getting the exact answer. Yeah. Yeah, so what I was calculating, what is the probability that you select AI, right? So when do you select AI? When you have selected at the ith step, you have selected AI, and then afterwards you don't select any of the next elements, because if we do, so each time we are selecting it, we are discarding whatever we have selected before. So we are just selecting one element. Okay. So you want to select AI and not select any of the ones that happen after it, that come after it. So the probability of selecting AI is 1 by I, okay, by definition. And then when the I plus 1 element comes in, with probability 1 over I plus 1 we select it, and with 1 minus 1 over I plus 1 we don't select it. Okay, because I mean in probability, if you are doing something with probability p, the probability of not doing it is 1 minus p. Okay. So with 1 minus 1 over I plus 1 you don't select it. Similarly with 1 minus 1 over I plus 2 you don't select ai plus 2. All the way up to am you don't want to select any of these, right? So with probability 1 minus 1 over m you don't select it, and you are taking the product because you want the event that the and of all these things happen. Right? You select ai and you don't select ai plus 1 and you don't select ai plus 2 and so on. And each of these are independent events. So in probability you can multiply the probability of these independent events, and when you do this calculation you find that basically so all these terms vanish. I mean, so all these numerator denominator pairs cancel out except for the last denominator, which is 1. Okay. You can also think of it intuitively, as I think you did. So you just say that each time you want to know what is the probability, what should be the probability of keeping that, right? And with that also you can come up with it. Okay. So this is reservoir sampling. So the next algorithm I am going to talk about, next problem is somewhat closer to distinct elements, but it's different. So the problem is called majority. Any questions? Okay. Right. So this problem is called majority. Okay. So the problem is as follows. So again you have a stream coming in. So the stream again may not be distinct items, so you can have some elements coming in as repeats. So the question is there any element which comes in more than half the time? And if so, we want to say. Okay. So in this in the solution I will give, if you don't have an algorithm, if you don't have a solution which is coming in more than half the time, then maybe you could return something else. Okay, but what the algorithm should do is, if you have an item which comes in more than m over 2 times, so m is the total length of the stream, the algorithm should return. So any suggestions about how to do this? So this is also a very classic algorithm. It was found in 1982. Yeah. Sorry, say it again. So
if the same element that is stored in the stream sketch, if that comes in increases
frequency, but
Yeah.
if any element comes, you decrease frequency by 1.
Yeah.
And if at any point it becomes 0, you take the fresh element. And if at the end any element is left, then it's the majority element.
Great. Okay.
But what if there is no majority element? Then the last element will be
Yeah, if there is no majority, then I mean this algorithm doesn't make any claim. So if the point is that if there is a majority, then it gives the right answer. Okay? So let me say it again for the purposes of everyone. So this is called so the Boyer and Moore in 82 gave this algorithm. So this is also a very classic algorithm. So one way of describing it is maybe here. So suppose you have a classroom, right? You have boys and girls. So I want to find if there are more boys than girls or if there are more girls than boys. Okay. So what the algorithm that was what's your name? Satish. So what Satish suggested is the following. So each time, so the stream of you are coming in an arbitrary order. Okay. So let's say that each time someone comes in, I make him stand here. Okay. And if there's so on this stage there will either always be all boys standing or all girls standing. Okay. So and they say initially a boy comes in, so he stands, and then if another boy comes in, then I make him stand also. Okay. And then if a girl comes in, I pair the boy with the girl and make them both go and sit down. Okay. So then I have one less boy on this stage. Okay. So similarly, so then if another girl comes in, then I pair the other boy also with the girl, and they go and sit down. So now there are 0 boys on the stage. So now if a girl comes in, I make her stand. Okay. If another girl comes in, I make her stand. And then if a boy comes in, I pair the boy with the girl and then I make them sit down. So then the number of girls goes down by 1. Okay. So this is the algorithm. So I mean intuition about why this works for people who haven't seen this algorithm before. So I want to say that if there are more boys than girls, then at the end there will be a boy standing. If there are more girls than boys, then at the end there will be a girl standing.
Pairing one matching the boy and the girl. So
Right.
if there is more, then they will be unpaired. So we will be standing.
Exactly. So yeah, it's a very simple algorithm, right? So yeah, so if there is a majority, it will be the case that I mean all the people who have sit down are sitting down in pairs, right? So if there is a majority, there will be at least one person standing up on the stage, and that person will have the majority gender. Does it make sense? So you can extend this algorithm. So maybe I'll write this down. So you have yeah. So it extends also to I mean. So here we just had 2 genders, but if you had multiple types of I mean items coming from I mean items could be some number between 1 to n instead of 1 and 2. You can also run the same algorithm. Okay. So you keep 2 things. So you keep in storage some item, okay, and you also keep a count. So let's call this item and count. Okay. So initially the count is 0 and this item is empty. There is no item. So so let's say when AI comes in, when AI arrives, if item equal to AI, so the thing that's being then count, then increment count. Okay. If item is not equal to AI but not empty either, but and item is not null, then decrement count. And if item is empty, so this bin is empty, then add AI to item. Does it make sense? So here we are keeping track of, so in the example I gave, so I am keeping track of whether it's a boy or a girl, and the count is keeping track of how many of these people are on stage. Okay. So initially I have no one on stage, so the count is 0. So when the first person comes in, I put him on stage and increment the count. So add AI to item and count equal to 1. My writing is really bad, but hopefully you understood what I meant. So initially when someone comes in, I make him the item and increment the count, and then if boys keep coming in, I keep the item the same, and then I just keep incrementing the count. And then when a girl comes in, so the item is not equal to AI, I decrement the count, meaning that I have paired those two people and off they go. So this goes on until the count becomes 0, so I have paired everyone off, and then the next person can become the item. Any questions about this? So as something for you to think about, you can think about how to generalize this to when, so here we are trying to distinguish when something has something occurs more than half times in the more than half of the times in the stream, right? So suppose you want to know whether something occurs more than say 10% of the time in the stream. How can you generalize this algorithm to take care of that? Any suggestions? Exactly. Yeah. So instead of pairing things, you keep 10 bins and you keep, or 9 bins and you do this. What do you mean? Element with maximum frequency. Yeah. So the next algorithm which I am going to talk about, and that's the most the one which will require most amount of work. So that will be for estimating the frequency of each item. Okay? So if you can estimate the frequency of every item with accuracy. Okay. So let's do that then. So this is so the next streaming algorithm I am going to talk about, it's called the count min sketch, and this is actually heavily used in many internet applications. So there are these databases, these streaming databases which people have built in order to deal with exactly the scenario I have told you earlier, where you need to count, say, the number of distinct elements, or you need to keep track of certain statistics of a stream. Okay, and so you store all of this in a database. So it's called a streaming database, meaning you don't really store the entire thing, but you store a sketch of the stream. Okay, and then you want to answer queries about the stream. Just like in a normal database, you store the entire thing and then you can ask queries out of it. In a streaming database, you store a sketch of the things and then you can answer queries about it. So it's a low space database essentially. So anyway, so let's talk about this problem. So this is called the frequency estimation problem. And here we'll find that we really need approximation and randomness. So the problem is as follows. So we will again have a stream A1 through AM. So let's define Fi to be the frequency of item I, meaning that the number of times, let's say Fj is the number of times J occurs in the stream. Okay, so right, so J is some number between 1 to n. So the stream A1 to AM is some number each of these is some number between 1 to n, right, as we said. So some integer between 1 to n. So you have F1 to Fn. Okay, so F1 is the number of times 1 occurs in the stream. f2 is the number of times 2 occurs in this stream, and so on. So if you had access to this, you could right, so you can find out whether some element is the majority by querying that element and seeing whether that occurs more than m by 2 times. And in general this is very useful because also, I mean, if you need to know whether some item occurs at all in the stream, you just need to say whether fj is more than 0 or not. Okay. Good. So we will give a solution to this problem. So okay, so let me so I will give the count min sketch . So this is by Graham Cormode and Shyam Muthukrishnan . From 2010, I think the first paper was in 2002, but it really took off after something like 2005. By the way, I did a postdoc at Rutgers University. So my advisor was Muthukrishnan. So he is one of the most amazing people I know. So he is said to be like in a quantum state. So no one knows where he is. So if you try to pin him down, he is in some other place. But somehow gets a lot of work done. So he lives a lot of time inside a jungle essentially with no power, and then he produces all these remarkable ideas. Okay, and it's somewhat coincidental that the initials of the authors is the same as the name of the sketch, CM. Okay. Okay, so here is the thing. So again, in this problem, so you want to give the right answer. So you don't know what will be asked. Okay, so you don't know j ahead of time, because if you knew j ahead of time, of course you could just keep track of how many times j is occurring in the stream. So you don't know whose frequency I will be asking. Okay. I want to construct some black. I mean, so right. So I want to, after this stream, then I want to take in. So then you give me j, and then I will answer what fj is. Okay. The question is clear. So intuitively, it seems that you actually here in this problem you actually need to. You need to almost store the entire stream, right? Because you almost need all of this information, and in fact you can make this precise. So you can show that if you have a deterministic scheme, meaning that you don't have any randomness, you need to answer the right, you need to give the right answer all the time, and you don't allow approximation. So fj has to be exactly correct. Then you actually need to store at least minimum of m or n amount of space. So the trick in this count min sketch is that how to get around these barriers. So you will use, so we will give the wrong answer some of the time and approximate fj in order to make sure, in order to get a huge amount of savings. Okay. So let me tell you the algorithm. Okay, so the algorithm is as follows. So I'll write it down as a theorem. Okay. So for any epsilon greater than 0, so you can take epsilon to be very small, something like 0.01. There is a sketching algorithm, a streaming algorithm using O of 1 by epsilon log 1 by epsilon space. So this is almost ridiculous. It's like constant amount of space. You're not even storing one element, such that so it returns some function okay, so such that okay, that returns there is a string that returns f hat, okay, such that f hat of f hat j is at least fj and at most fj plus epsilon m. Okay, sorry. Maybe I'll, sorry. So this is so for any. Okay, so with probability at least 1 minus epsilon. Sorry. With probability at least. Okay. So I just want to take a couple of minutes explaining this, because many of you have not seen randomization really in the context of algorithms. So what this is saying is that this algorithm, so the algorithm has two steps, right? It takes in the stream. So when it's taking in the stream, it's forming some sketch. So it's maintaining this sketch incrementally, okay? And then after this stream has been finished, you ask for it j, and in this case it returns f hat j. Okay. So the claim is that so with probability at least 1 minus epsilon. So think of epsilon as 0.01. So for concreteness, so this is 1 minus epsilon is 0.9999%. So with 99% probability, it's the case that for every j, okay, it returns an estimate which is off from which is more than the real frequency by at most 0.01 m. Does it make sense? So the frequency can at most be m. So you are estimating the frequency up to some relative error which is 0.01. So up to this 0.01 m error, you will be returning the right answer. You will be returning the right answer, and with 99% probability, this is true for all j. So it's not the case that for some j it's true and for some j it's not true. So you have this much error maybe during the operation of your of making the sketch, okay. But then when the sketch is done with 99% probability, for every j you will get an estimate which is valid to within 0.01 relative error. M is the m is the total number of elements. So the frequency can be maximum at most m. Okay. So this is almost ridiculous, right? I mean, so the space that's being used is constant. So if epsilon is 0.01, this is like 100 times log of 100, so 200. So some 200 is nothing in for a computer to store, right? So some in order of, so with constant space we are able to actually give the correct answer within some given relative error. So this is not even space to store one element. Okay, so let's see how this works. The algorithm is also remarkably simple to describe. The analysis is also not too hard. It seems almost like magic that this works. Okay. Okay, so the first thing to do, okay, so let's just define two parameters. So I will say D. So D is this log of 1 by epsilon. Okay. So this is log base 2. And let's also define the parameter W. W is 2 divided by epsilon. Okay. So in particular, when epsilon is 0.01, this is log base 2 of 100, which is, I guess, 6 point something, and W is 200. So now I will construct a table. So the sketch that I am going to maintain is a table which is of height W and length and width D. Okay. Sorry, width D and height W. And what am I going to store here? So that's the amount of space, right? So this explains why this is taking off 1 by epsilon log of 1 by epsilon space, because here it's 1 by epsilon log of 1 by epsilon. And now what am I going to store? So here I'm going to choose D functions. So choose D. So okay, so I have to explain this. So I'll come back to this after I finish the analysis of the algorithms. But suppose that somehow you choose D random functions. So these are hash functions, h1 to hd. So they take, go from, so each hi, so each h1 to hd maps 1 to n to 1 through w. Okay. Does this make sense? Okay. So these will be random functions. So I have to tell you later on how to actually, I mean, somehow you need to store random functions, okay? And it's not very easy storing random functions, because if you think about it, each hi needs to be described some way, okay? And you can't keep in your storage a truth table, because storing hi would itself require then n amount of storage, right? Because you need to know what h of 1 is, h of 2 is, h of 3 is, h of 4 is, and we are assuming that n is very large. So we can't really manage to keep in hand the truth table or the evaluation table of each of the HIs, but I will find some other way to describe the HIs in such a way that they behave somewhat randomly. So I will say what again I mean by random later on. But suppose we have this, okay. So then what is the algorithm? So the algorithm, let's say this is call it update of A. So this is what happens when when the stream gets when the algorithm gets A in the stream. So when the next item is A. So how do I update this? So initially this matrix is all zeros, and each time I get an update I do something. So suppose I get the item A, okay. Then what do? Then I increment. So for I equal to 1 to D, increment increment, so let's call this table T, or maybe let's call it CM in honor of Kormod and Muthukrishnan. So increment CM of right, so I have to, so CM of H of A I. So this is the row index, this is the column index. So if you have any questions, please ask me, so that I mean, if there is a confusion, then we can all learn from it. Okay. So initially these are all zeros, and then each time, so think about some specific I. So what I am doing is I am looking at what, sorry, this is hi of A. So I am looking at what A maps to in hi. So if you think of it as a hash function, you look at what A hashes to according to hi. Okay, and then I increment. So in that column, so for example, for I equal to 1, I look at what is h1 of A. Okay, and then so h1 of A is something, and then I increment the entry here. h2 of A is going to be something else, then I increment the index here. h3 of A is going to be something else, then I increment the entry here, and so on. It's a very simple algorithm, right? Nothing much. So this is the update. So this is what this storage does. And then how do I find, so what is the estimator? Okay, maybe let's look at, so I will take 5 more minutes. Okay. So what is a property of this table? So it should be the case. So you think about it. So now suppose you are trying to find the frequency of item A at the end of this tree. Okay. So whenever item A has occurred, I have updated hi of A at column I, right? So I have updated h1 of A in column 1, h2 of A in column 2, h3 of A in column 3, and so on. So it must be, but the problem, of course, what could happen is that something other than A could also have hashed to the same location. Right? So each of these is going to be at least what the frequency of A is. But it could be more. Okay. But the idea, so our estimate is going to be the minimum of all these hi of A. Okay. So the claim is that there is going to be one hi of A which is actually going to be pretty close to the real frequency. Okay. So this is the write these smaller. So d is log base 2 of 1 by epsilon, and w was 2 by epsilon, and right. So f. So I'll define f hat j to be the minimum. Let's say f hat a to be the minimum over all I. So I from 1 to d of Cm of hi of A, hi of A Does it make sense? So this part is clear, right? Why fj hat is going to be at least fj, because the estimated frequency is always going to be at least more, but the problem is that other items could also have hashed to the same location, in which case this could be much more, but the claim is that it's not going to be much more with constant probability, I mean with probability at least 99%. So let's see why this is true. So let me maybe actually erase this, but I think we already know, so we need to prove this. So we will erase everything other than so this is what we need to prove. Right. So let's say, right, so let's look at what's the expected difference. So expected in right. So that's one notation. So this is expectation if I am thinking of these H1 to Hd as being random. Okay. So if they are random functions, what is the, so this f I should define. So let's say, what is the difference between Cm of Hi of A I from Fa, right? So this, as we said, this can be much more, but we want to bound the difference. So for any given I. Okay. So then this is equal to, so when can it be? As we said, the only way, I mean it can be more, is if some other B also hashes to the same position as A, right? So let's look at all possible B which is not at A. So it can be basically, so you can count FB also if it's the case. Yeah, so I'll introduce this notation. Yeah, so I'll introduce this notation FB. So I of Hi of A is equal to Hi of. So this is called an indicator function. So what this is saying, so what is this? So this is saying that this difference, so if it's the case that Hi of A is equal to Hi of B, right, then FB contributes to this sum. And if Hi of A is not equal to Hi of B, then FB doesn't contribute to this sum, right? So this is, this notation, so this is 1 if Hi of A is equal to Hi of B and 0 otherwise. So I just want to make sure that, so I am just writing it down formally what I said. Okay. So now there is this property called linearity of expectations. So you can take this expectation and put it inside. Okay. So this is, take B not equal to A, FB. So the only probability is coming in here. So because we are choosing these random functions, so I need to make sure, so what is the, okay. So I mean this part doesn't involve any randomness. So the only randomness was in choosing these HIs, right? So I am looking at the expected number of times you have, so for any B, what is the, so this is essentially the probability that Hi of A is equal to Hi of B. Okay. So I will just erase this and say what is the probability. So FB times probability that Hi of A is equal to Hi of B. And now if these are truly random functions, the probability that two things hash to the same value is 1 by W. Okay. So you are mapping each of these things to a random element in W from 1 to W. So if you have, so A maps to something, the probability that some B maps to the same thing is 1 over W, right. So this is at most, so this is 1 by W, so this is at most M by W. W was delta by 2, right. So this is at most, so this is equal to delta M by 2. Okay. So this is on average, what is the probability that this estimate, how much you overestimate Fa. Okay. So now I'll just quickly wrap this up. So now what happens is that so this is for average over HIs, but now we have chosen particular HIs, right. So for a particular HI, what is the probability? So if the average is at most, so if the expected value of this difference is at most delta M by 2, okay, then it follows then the probability that CMHI of AI is more than delta m is less than equal to half. Okay. Why? Because if you think about it, if it was the case that more than half, with more than half probability, this overestimate was more than delta m, then the expected value of the overestimate would have been more than delta m. Whereas here we said that the overestimate is the expected value of the overestimate is at most delta m by 2. Okay. So with probability 1 by 2, with probability half, it's the case that for each of the HIs, the estimate is more than delta m is at most half. Okay. And now FA is the minimum of this. So the minimum can be, so the minimum of the overestimates is more than delta m is at most 1 by 2 to the power of d. Right. So the probability that f hat of a minus fa, so f hat a minus fa is more than delta m is at most 1 by 2 to the power of d, because you need, for all of the d hash functions, you have so much overestimate. Okay. This was for some particular I, but this fa is, you are taking the minimum. So the minimum can be overestimate if for all of the i's, the overestimate according to hi is more than delta m. So this is more than 1 by 2 to the d, and d was chosen to be this log of 1 by epsilon. So this is epsilon. Okay. So the probability that the overestimate is more than, I use delta instead of epsilon, and I hope you can. So this m by w should have been, so w was 1 by epsilon, right, not delta. This was epsilon. All of this, all the deltas are epsilon. So the probability that the overestimate is more than epsilon m is at most epsilon, which is exactly what we wanted to prove. Okay. So the only other hitch here is that you are choosing random functions, and random functions, as we said, is very hard to describe, because even describing them takes a lot of space. The issue, the way to get around it is to notice that this is not truly random. You just need that two different points collide with probability 1 by w, and these types of hash functions are known. These are called universal hash functions, and you can, and perhaps you have talked about them in your algorithms class. Okay. Anyway, you can look up pairwise independent hash functions, and they basically can be used to solve this problem in a space that I can. Okay.
Any questions, sir?
Yeah. There are some similarities with Bloom filtering, but right. But in the streaming context, this algorithm was the first that was done in this way. Yeah. Any other questions?
Thank you very much, sir, for your nice talk.